Welcome to the presentation of Team26. In our project, we apply state-of-art methods to distill language model. Our presentation is divided into 6 parts. Why we chose these topics? Transformer-based supervised learning model has shown impressive results in various speech types, but their large size and high computational demands hinder the use of resource-constrained environments. Our research aims to provide more accessible and affordable advanced speech technology. Why did we choose this paper? Star, the winner of the best student paper at ACAS 2022, is the leading distillation methods. Innovatively reduce computational complexity while maintaining higher performance by focusing on temporal relation between speech frames. For our test, we use public dataset and an open source teacher model. Since the code is not provided, we reproduce this paper's result by distilling the teacher model and evaluating on a university benchmark. Next, Qingzhen will discuss approach and methods.
Well, directly learning the teacher's detailed frame-level representations is quite difficult. To solve this, the baseline model introduces two flexible distillation strategies. First is distilling the knowledge via the average intention map, and second is capturing temporal relations between speech frames. In detail, the baseline model utilizes Hubert as the teacher's model, which is composed of a salient feature extractor and several transformer layers. The student model has the same architecture with the teacher model, but it reduces the width of the attention layers and the feed-forward networks, resulting in less parameters. To efficiently distill the teacher's model, the baseline method first distills the attention maps. It averages the attention maps across all heads and computes the K divergence between teacher and student. Then it computes the L2 divergence between the teacher and student's model's temporal matrix of each layer's representation, which is served as the layer-wise temporal relation loss. To offer more flexible distillation, the model also computes the temporal relation between the input and the output of the single layer, and distills this interlayer temporal matrix. This kind of distillation captures the progression of speech representation within each individual layer. In our experiments, we only focus solely on the temporal relationship distillation, and it's the core method and of the original mapper. So, and the original mapper also shows that the distilling attention maps is in fact ineffective. So we choose to only use the temporal relationship.
Let me introduce the implementation and experiment part. For training detail, the student model was trained on labor speech trained data for 200 epochs. We used the Hubert base as teacher model, AdamW as optimizer with a warm-up cosine scheduler. For loss selection, the total loss equals to the sum of layer-wise loss and the inter-layer loss, which measures the difference between student model and teacher models. We use the super benchmark to evaluate our student model. This benchmark tests the models on various speech-related tasks and enable us to assess how well the distilled model representations generate across different aspects of speech. Here we list all the evaluation tasks. Then we can see the metrics for each task. We have underlined our results and those from original paper. This shows our results are very similar to those in the original papers.
Given these outcomes, the next step we think is to improve the loss design and better reduce parameters. In refining our distillation approach, we are focusing on how the loss function guides learnings. Currently, we equal weight layer-wise and intra-layer temporal relations, but adjusting their balance or adding new constraints may better capture the teacher's structure. And we are also considering adaptive weighting strategies or even contrastive loss to ensure the student retain critical temporal patterns while remaining efficient. Rather than simply shrinking each layer uniformly, we are looking at structure pruning to remove parameters that matter less, preserving key information while lowering computational cost. Additionally, we may apply architecture search techniques to identify configurations that maintain essential temporal relations while making the model more resource-friendly. To conclude, in this project, we reproduced the star distillation method and trained our model longer to see if we could bridge the performance gap and will achieve an overall similar performance. Moving forward, we think refine our loss design, embracing more sophisticated parameter reduction strategies, and evaluate additional tasks that helps improving the model. These steps aim to create a truly compact, high-performance, and speech model that bring advanced speech representation to resource-limited environment. Thank you.